Welcome to Calibrated, a webcast about uncertainty, Bayesian inference, and machine learning. I'm your host, Eric Novik, and I'm very excited to have Rock Češnovar joining us today from Slovenia. Welcome to the program, Rock.
Hi.
Yeah, we're excited to have you. So currently you're a researcher at the Faculty of Computer Information Science at the University of Ljubljana, and you do a lot of stuff with Bayes and Stand. But first, how did you encounter Bayes? How did you find it?
Well, I was basically a failed PhD student like 5 years ago. I was mostly interested in GPUs, parallel programming, so not statistics, not Bayesian statistics, nothing of that sorts. And then Eric Strumbel, professor here in our faculty, came basically in our lab and said, do you want to add GPU support to Stan? And I was like, okay, what's Stan? And then we got into that story, Bayesian statistics, Stan, what's Stan, how useful it is, how many people use it, what kind of problems it solves, and so forth. And I got really interested in it. At first, adding GPU support, then contributing on various submodules across Stan, from the language side to the interfaces. That got me interested deeply into Stan.
You got to Bayes from Stan, not the other way around.
Yeah, so basically I started in the learning the automatic differentiation in StandMath, which is all I needed to know at that time, which was also like the first step in our journey of adding GPU support. Then grew from that to the language side and the rest.
Interesting. I'm curious, like, what attracted you to it? I mean, you're a computer scientist, correct? And so you know lots of languages, computer languages, I presume. And so what was it about Stan that kind of attracted you, and like, why do you spend so much time working on it?
Yeah, I mean, what attracted me was I wanted I saw how useful it is, and we wanted to add like GPU support, and then also I enjoyed like the that it's so diverse. So you have the language side, you have the parser, you have the code generation that translate to C++. Then you have a bunch of highly optimized C++ code that's really interesting to both read and write and to like dive into. It has various different sub projects in it that you can like jump if you get bored. Essentially, working on some parts of it, you can go work on something else that's completely different, but still inside like the Stan ecosystem.
Yeah. And does this intersect with your core research? Because you're a PhD student, right? Are you completing?
Yeah, I'm finishing. I'm hopefully finishing in like a month or so. The GPU support that I along with my colleagues like today and Steve, that we added the GPU support. So part of that addition of GPU support is my thesis with a bunch of like other minor stuff. So it's closely related. So I started with a different topic, and as I said, I failed with that one. And then like working on Stan really got me working on an actual project instead of like working on a paper that's not even your advisor is going to read. Made me more interested in working on and finishing my PhD. Essentially.
Interesting. Okay, I wonder if you could talk a little bit about what it was like to become a contributor to Stan. Where were some of the difficulties in getting started, and how did you ultimately become a productive member of the Stan development team?
So we started basically writing on pull requests or issues out of the blue. I was like, my GitHub account was essentially empty. I made no contributions before that. We started browsing the StandMat library, starting reading the issues. I saw that Steve Ronder was also interested in adding GPU support, so I kind of started commenting on the pull requests, debating mostly at the start. Then we sent like an email to Professor Gelman, to Bob Carpenter, Daniel Lee, who also was with you with General. And they were all really nice and supportive in like welcoming us, helping us set up everything we need, describing the code, like guiding us through it, everything we needed. So that was really a pleasurable experience. And that's probably gist of it, how we started. And then I got to know the rest of the developers at that time, Sean Tolls, Ben Bales, who were all really, really, really nice and really supportive and really wanted to help me help them, essentially.
Yeah, that's great. That's great to hear. The last question I want to ask, before we turn it over to you is, if someone wants to start contributing to Stan, and maybe they're not as experienced in, C++ or some of the deeper technologies as you are, what would you recommend they do to get started?
So yeah, I wouldn't call myself, at the start, I was definitely not deeply into like stuff like C++. I mostly used C before, so it's not really a requirement to have a deep knowledge in C++ or any of the languages used in Stan. Like if you're interested in high performance computer or performance, then maybe focus on C++. Browse the code, see where you can help. There's like a lot of good first issues. Just comment there. Even if you don't really know like even the half of how you would tackle it, but you want to start working on it, just post there. There's a bunch of people that are going to be eager to help you get started. I think that's one of the experiences we try to make for newcomers, that we try to help them anyway. Like we can set up a call, we can describe whatever you need to get started. And so if you like C++, maybe start with StandMath. If you're a compiler developer, like if you like developer compilers, maybe start on the Stan language side, the Stan C3 submodule. If you're more into math or stuff like that, it's also StandMat library, probably the best one. If you're into sampling algorithms, the StandCore module is the way to go. Also, you can contribute by writing docs, which is also very, 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 very helpful. And Stan is probably one of the things that's most known for is the vast documentation it provides. So there's various areas. Like you don't need to know C++. If you don't know C++, that's definitely not a showstopper. So, and definitely don't be discouraged, even if you don't know any of the languages in detail. We can help you along the way. That's how I started.
Cool. Well, that's very helpful. Thank you. So with that, I'm going to turn it over to you. For everyone else, if you have questions for Rock, please post them in the stage chat, where I think a lot of people have been posting, so this is the right place to do it. We will address them possibly during the talk, and perhaps we'll hold a few towards the end. So take it away, Rock.
So I'm just going to go quickly over what we're going to learn today. First, I'm going to start by describing the core modules of Stan. So how do they fit together? What are they? And how do the interfaces make them work? So like the users can actually use those core modules. I'm going to then highlight a couple of features that were added in the last year, or maybe 2 years. Show some tips and tricks, the low-hanging fruit you can try out that can easily make your Stan model run faster. And finally, we're going to see some of the features that are currently in the pipeline and will probably make it to Stan, hopefully, or most likely into Stan in like the next year or so. In order to make a Bayesian inference framework or a tool, you need three things. You need a language with which you can describe a model. You need a sampling algorithm that can sample with that model description. And you need a automatic differentiation library which can sample. Because like most of the state-of-the-art or all of the state-of-the-art samplers require gradients. So we have all three of those. We have the Stan language, which is which is handled by the Stan C3 submodule, which is a Stan to C++ compiler. So that's the module that takes your Stan model and compiles it into C++. Then we have the Stan module that has the dynamic HMC sampler, which also has all the other sampling algorithms we support, including variation inference and also optimization algorithms. And finally, the automatic differentiation is supported in the StandMat library. So we're going to start with the StandMat library, then see how that interacts with StandC3, and finally how that interacts with Stand. So the user starts writing with their model, which is inputted into the StandC3 compiler or transpiler, whatever you want to call it. That produces a C++ model, which is manifested as a C++ class, which includes the entire StandMat library because it also needs it. And then separately, we have the StandCore, which has the samplers and all the other machinery we need in order to run it. Then that gets combined in different ways in different interfaces. And with a C++ compiler, it produces various forms of runnable executables, which are inputted, to which we input data, sampling configurations. So the sampling configurations are the settings for the sampling algorithm. Optionally, we set initial values, and finally, we get out the samples. So this is the whole story. The difference between the various interfaces, like, is here. How do they combine the C++ model, StandMath, Stand, and what do they produce with the C++ compiler? So the basic idea of the StandMat library is automatic differentiation with operator overloading. Don't get too scared. Don't run away right now. The basic idea is we have a expression like f is a times b, and so forth. And we want to say that a and c are parameters or variables in our function. So we need to compute the gradient with respect to them. And b is a constant. Here, b is an integer, but it might as well be a double constant. That doesn't really make a difference here. So what we do in order to make those a and c variables, we define them as vars. Var is a special class in StandMath library which holds the value and adjoint of the variable. So in essence, at the final step, it will hold the adjoint values will represent the gradient with respect to the function. We can see that now a and c are vars. B was left the simple C++ integer. We run that expression, call f.grad on the result, which computes the entire gradient, and then we can access those values, the function value or the gradients with the adjoint function or all the vars. So this is the gist that makes all the stand samplers run, because we need the gradient evaluations. All functions must support the var argument and must have derivatives defined. So you can imagine that is a lot of code, which you would be true if you did imagine that. That's a lot of code, because you need to, like, in addition to handling the simple case of multiplying two constants, which you can also do in C++, regular C++, you need to have a definition of multiplying two variables. But in addition to that, you also need to cover the other two cases where one input is a variable and the other is a constant. You need to handle all those cases, which makes the StandMath library a big project and a lot of code, and also a lot of code to test. In addition to scholars, we also support parameter and data containers, which can be represented in two forms: either as a vector, as a standard vector, which is a part of the standard C++ library, where the type can be integer, double, or another vector, or an eigen matrix. An eigen is a C++ library highly optimized for linear algebra, and we'll see how that translates to Stand. Again, the template type can here be both a constant as well as a variable. All that is used to run reverse mode automatic differentiation. So when this line runs, you will the expression graph is constructed. So the entire graph is constructed, and from bottom up. And then once the grad function is called, you go the reverse way. In the reverse pass, all the gradients are So the entire gradient is computed in a single pass, which makes this a perfect automatic differentiation approach for Stand, because Stand has a single output function, which is the target function.
Rock, I'd like to ask a question that's brought up by Bruno Nissenboim. He asked, I got lost in what's the difference between var and double. Can you just like explain the var concept?
So you will see. So the double, like a C++ double or a C++ integer, is a translation of a data variable in Stand. So it's a constant, and a var represents a parameter. Okay, does that answer the question? So if you specify the input as a double or an integer, you will not get the gradient, which is essentially the hopefully that's
that should make sense. Thank you.
Okay, thanks, Bruno. So this is precisely the intro to this type of talk. So yeah, how this plays with Stan. As I said before, StandC3 translates the Stan model to a C++ class that represents the model. First, let's look at the data type translation. An integer in Stan is translated into an integer in C++. A real is translated directly into a double. A vector, so in this case, if it's a data type. If it's a data type, the real isn't translated into a double. A vector is translated into an eigenvector. Row vector is translated into a row vector in the eigen library, same as for the matrix. If it's an array type, you need to, that will translate into a standard vector. If it's a parameter, obviously the integers do not get translated because Stan does not support integer parameters. Reals will get translated directly into scalar, single objects of the var class. Then a vector is a eigenvector of vars, a row vector is an eigen row vector of vars, and so on. Similar for the standard vector, which can also, like array of reals will be a standard vector of vars. And then that's like the basic story. Then if we have an example model, which is the red card model that's commonly seen, that gets translated, the data block gets translated into private members of the C++ class. I didn't mention before, the StandC3 compiler is written in OCaml, which is a functional programming language. That's like a side story. So let's continue. So yeah, the data variables are translated into private members of the class. As we see here, integer is an integer, or an array of integers is a standard vector of integers, and so forth. The model constructor reads in the data variables, so it reads in the values for the red cards, the games, and the rating, and optionally also runs the data transforms if you define any transform data in your model. So that runs only once because it only runs in the models, in the C++ class constructor, which represents the model. Then we get to the fun part. The fun part is translating everything else. So the parameters, transform parameters, and the model block are implemented in the logprop member function, which uses the functions in StandMat because it needs the gradients. So a beta parameter, which is a vector of 2 elements, is represented as a eigenmatrix, and the type here is noted as T, but this T is typically var. And all the rest of the machinery, so this is an accumulator for the logprop value, so the LP value, and this deserializer is used to read in the new values selected by the sampler. So these are written into the beta matrix, or the vector, and then we get to the model part. You will see that the normal LPDF function is translated into a normal LPDM C++ function. Binomial logit is also translated into binomial logit LPMF function. All of these are added to the accumulator, and if you are looking closely, you will see that the difference is here you will have a false template parameter, here you have a prop. The difference is because this is written as the first line is written as a target plus, and the second one is written as with a tilde sampling statement. As you probably know, the sampling statement drops the constant, and that's done by defining the template parameters. Then all the other arguments are simply listed as C++ parameters. Here I wrote this a bit simplified. So this is beta, the beta 0, beta 1, and multiplied by rating. It's not really that simple. So if you don't, the 1 is not translated into 0, 2 is not translated directly into 1. It's done a bit more complex with an R value function that handles indexings, which basically takes care if you make a mistake, try to index something that doesn't exist, that R value function will let you know. And also the string here is used in the error message. And that's basically it. That's the gist of what the StandC3 model has to do. The stand module then uses this model, calls the logprop function inside either the dynamic HMC, the VI algorithm, or various optimization algorithms. In addition to that, the stand submodule also has R value and assign functions, the R value function. So these are all helper functions that make the communication between the sampler and the StandMat library easier. And also handle like user-facing stuff like error messaging and stuff like that. Okay, so let's see how those things come to life in various interfaces. As I said before, this picture represents what's missing in this picture is how do we combine the module and stand, and what do we produce with the C++ compiler. So we're gonna, and how do all of these stand model, initial values, data, samples, how are they input, or what do they input? What do the output, or what does the output look like? So let's first start with the command stand, which is a command line interface. For command stand, the compiled model, so this cloud here is actually a executable file, so a .exe file if you're running Windows, or a non-suffixed file if you're running Unix systems. The combining of the core modules is done with standard C++. No additional libraries are needed except for stuff like reading JSON files. StandC3 is shipped as a binary executable with command stand releases. So the StandC3 OCaml code is compiled into a binary, and the stand model is supplied as a stand file, as a .stand file. Data is supplied as a JSON or RDAM file. Initial values and sampling configuration are supplied as command line arguments. Initial values can also be in files. And finally, the samples are produced as CSV files. The releases are available on the link that you hopefully already know. So what are some of the benefits of using command stand? It has the fastest compile times that we'll see a bit later. It's easiest to fine-tune performance with all of the exotic C++ compiler flags. It's the only interface you can use with stuff like MPI or other libraries. It's the only interface we daily test with in our continuous integration. So it's definitely the most tested one. But it has a slower input-output parsing and outputting. I mean, slower, but for instance, it takes 20 seconds to output 1,000 samples for 50K parameters, which isn't a lot. Typically, a model with 50K parameters, 20 seconds for that big of a model is not going to be crucial for you. If it is, this probably isn't in the interface for you. Luckily, we have more. So I'm going to next present the rstand and the rstand version 2.26, which is the next version that's going to come out. As you probably know, rstand is a bit behind because there were significant changes in the development. So in rstand 2.26 and beyond, this part was actually the same as before. The compiled model is represented as an object file, which is linked with R. The combining happens again with C++ with some additional RCPP code that makes that C++ interact with R. The stance3 is a JavaScript file. So the opencl can also be translated into JavaScript. The model is represented as a string, which is inputted into this JavaScript compiler. And all the rest, like data, initial values, sampling configurations, are objects one way or the other. And the samples are also R objects. The rstand226 is not currently available on CRAN for various reasons that maybe if someone's interested, we can go into later. You can install it, but you can install it from our StandDev repository. The instructions are written on the slide. This was a significant overhaul because the compiler, the stand to C++ compiler, was previously written in C++ and is now written in opencl. And that change meant that we had to do a bunch of work, which is finally resulted into rstand lagging a bit behind. The good side of rstand, in addition to faster input-output, is it also provides some additional, more tightly bonded functionalities, like accessing to logprop function directly, so you can access the model's member function directly. You can use stuff like grad logprop, unconstrained parse, expose, user-defined functions, stuff like that. PyStand was also significantly overhauled and is split into two parts: httpstand, which does all the dirty work, so interfacing with stand. So the interfacing with Python and C++ is let's call it a nightmare. And it has a HTTP REST-like interface. So if you are familiar with REST interfaces, it's essentially get, post HTTP requests to do various tasks. Then PyStand3 is essentially just a Python-only package that makes HTTP requests to httpstand. PyStand3, much like rstand, provides a few additional tightly coupled functionalities like logprop and stuff like that. It only supports the dynamic HMC sampler because it was, as I said, overhauled and the development just hasn't caught up. And it also supports only Linux and Mac OS right now. So let's look quickly into that. So in httpstand, the compiled model is again an object file linked into Python. The modules are combined with C++ with a splash of Cython. stance3 is, much like in CommandStand, a binary shipped with the release. So this should be a PyStand, the HTTP release. The stand model is inputted as a string in an HTTP request, much like the rest of the inputs. So data, initial values, sampling configurations. These are all HTTP request body objects. And the samplers are outputted as a JSON in the HTTP request. So httpstand does all the dirty work, so PyStand doesn't have to do any of these. It doesn't have to compile, it just delegates it to httpstand. The stand model is a string that's sent to httpstand, and all the other inputs and outputs are Python objects or arguments. This was done primarily because it's much easier to develop the user-facing stuff in PyStand without having to rebuild all the machinery that makes Python and C++ stuff work. Okay, so finally, I'm going to talk about the lightweight wrappers for CommandStand, which take all the benefits and drawbacks of CommandStand and combine that with ease of using R and Python directly as opposed to the command line. These interfaces are a bit less or completely not tightly coupled with R and Python. So R and Python and the Stand C++ are definitely not tightly coupled here. But that makes it easier to detect and handle issues because we're a bit on the higher side. We can do seamless version updates. So essentially, when a new version of CommandStand comes out, that's it. It provides access to MPI opencl capabilities, which rstand and PyStand currently do not. But it lacks some of the tightly coupled features like logprop and stuff like that. The compiled model is a CommandStand executable the models are combined again with standard C++. Things are similar to how we handle them in command stand, except for the data initial values configuring the sampler are all are Python objects. The samplers are produced as CSV files that are afterwards read into our own Python environments. Okay, that was a quick rundown of the various interfaces. If anyone is interested in any of them, we can talk about it later. But I'm going to now spend a few minutes describing a bit of some of the features that were added in the last few versions. The first one is using expression templating. This is like a deep C++ feature. If you don't care about the C++ side, only know that this makes your model run faster. The idea is that instead of like a function x plus y returning the result, so the actual result in a vector or a scalar, it returns an object that represents the expression. So instead of computing x plus x directly, we say, okay, this returns a addition of x plus x. This returns the multiplication. And finally, once we figure out now we really need the result, we actually do the entire computation in one go. That's like a standard optimization technique used in the Eigen library. This significantly decreases the amount of memory copies that we need to do, because if you compute x plus x, you store it in the memory as a temp1 variable. Y times y is also stored as a temporary variable, and then finally summed together, which is again stored in a temporary variable. This is all done in one go, which makes it much more memory efficient. This means directly for the users that the functions that use data and functions in the generated quantities are much faster now, especially like small vectors, small matrices. If you do a bunch of computations with small matrices, that should be like at least 20-30% faster, sometimes even a bit more. But that also meant that we could, which is probably a bigger story here, that we were able to speed up all log probability functions, all log probability mass functions, because those functions are more complex and they use a bunch of expressions that are complex, obviously. And avoiding memory copies there was also very, very crucial. This brought like a 20-30% or even more for some of these log probability mass and density functions, which this was added into the release 2.25. And at that time, we measured like most of the log probability functions we tested were like 20-30%, or at least for smaller sizes were around 20-30% faster at that time. The next feature that was added, part of this feature was added even I think in version 2.19, so it has a long beard, as we say. So the idea is, instead of writing this expression Bernoulli logic alpha plus beta times x, you specify a GLM function. So you only supplied the 3 arguments, and this all computation is done inside it. So if we go back to the expression tree I showed before, this essentially means that we combine the nodes in an expression tree into a big node. This approach is sometimes called, I think, supernode or big nodes, or something. Previous versions of Stan had the Bernoulli logic, neg binomial, normal ID, and Poisson log functions. We added additionally categorical logic and ordered logistic GLM functions, but the first 4 were also significantly overhauled and are much faster as a result now. So the takeaway here is, on the next slide, if you can use any of these GLM functions, do use them a lot, because as we see, even in the worst cases, the speed up is around 50%. Best case for the ordinal regression GLM function, the speedup is around 30. For the softmax regression, so the categorical logic, the speedup is even higher. So worst case, you get a 10 times speedup. Best case, you're closer to 50. So if you can use these, if these are applicable in your model, do use them as we've shown before. So the speedups for the rest of the 4 are in this neighborhood. The next feature I want to highlight is profiling. This makes, so with this functionality, you can identify the bottlenecks in your model more efficiently. Problem is, so if you change a line in your model, it's typically hard to know what kind of effect that had because of the stochastic nature of your model. The sampler, because of the numerical differences, the sample goes another way, and it's difficult to decipher how much did your change contribute. So you can write your, so the lines of the stand model you care about, you can encapsulate them in a profile section, and then you will get the total times the computation was spent, the execution time was wasted or spent in that part of your model, and also the number of the auto-diff calls that were made. This means you can actually see the per gradient numbers, so the per gradient execution times, which are much more stable, which means just running your warm-up for like 10 iterations, you will see stable results, and you will see if your gradient times have been improved, how much did you improve your section, and stuff like that. This can be helpful, as is listed here, to evaluate bottlenecks, to identify parts of your model that you can parallelize, or maybe rewrite with a different function, reparameterize, stuff like that. There's also a couple of language features, which I'm going to show in, if you ever worked with the old ODE interface, you may remember that you had to, the old interface, yeah. You may remember that you had to pack your variables, pack the parameters, and input those parameters here. And which also meant you had to unpack them in the ODE function. So you had to unpack, name them correctly. The new ODE interface does not require that much work. So you just input, I'm being silly. So the new interface, you just list your variables. Those variables are automatically listed. You can list them here without packing, and you can use them directly in your function. This simplifies in the code, makes it much more readable, and I think, as far as I remember, also a touch fast because of the underlying changes, not because of the language side of changes. Another change that's been added was a new array syntax. I like this one a lot, simply because I didn't find this syntax very readable. So this is the old way of describing an integer array, and this is now the new way of describing an integer array. You can also, so this new syntax is mostly useful because of like an array of vectors is now much easier to decipher what dimension, how big is the dimension of the vector or the array. The old array syntax is going away in about a year or so. So if you can, try to adjust to the new array syntax, which I honestly, for myself, think it's a lot faster, a lot nicer. So we're going to get to a few other language features a bit later. The last one I'm going to mention here is the reducedsum, or the within chain parallelization. Imagine that we have a binomial logic function. This again, the red card example. We list the inputs, and we would then just rewrite this function in a user-defined function. So this is the same module, the same function, just called inside a user defined function. If you can see here, it's precisely the same. Now what we do, we say, okay, the first argument, which is the red cards here, we're going to slice it. So each call of this function is going to get only a slice of it. And the rest of the arguments are going to be exactly the same as they were. So we rename that to slice red cards, and we get 2 additional arguments, start and end of the slice. So each call of the partial sum function is going to get a slice of the first argument. And we then compute, okay, just a part of the binomial logic LPMF function. We use the slice. We use indexing to get the parts of the rest of the arguments. So the games we need to index from start to end because we only need a part. So, and why would we do that? Because this is actually split into multiple threads. Each thread essentially computing the partial sum function for a slice. This is done with the reducedsum function, to which we input the partial sum, so the name of the function and the arguments. The grain size here represents how big those slices do we want to make. So how big do we want to make those slices? The within temporalization is nice because it requires no additional flags, no additional installation. The library we used for parallelization, the Intel TBB, is bundled with StandMat, essentially, and then also Stand. I mentioned earlier that we improved a ton compile times in version 2.19. So these are command stand numbers, because the faster compilation is mostly seen in command stand, a bit also other ways in other interfaces, but command stand benefited here the most. So we can see that the final numbers, so these are 3 different models. The 8 schools one is obviously the less complex, and the hierarchical GP model is the most complex one here. We can see that over the years, we have made it like the simple model compilation, like here, it's 4 times faster, while the more complex one are still faster for like a factor of 2 or close there. Obviously, compilation can still take quite some time because the C++ compiler has a lot of code to work with. As I said before, the StandMath library is complex because it has to be. Okay, so that was a rundown of the features that were added recently. There were obviously tons more, but there's only a finite amount of time we have. So a few quick tips and tricks. So these are the low-hanging fruits you can pick. Use vectors instead of arrays wherever applicable. I've seen users using arrays of reals instead of vectors, and that's if it's not needed, it's inefficient. At least at minimum like 10% or maybe even more, 20%, stuff like that. Expression templating is only applicable to vectors because they are represented as eigen vectors. The eigen functions are also faster because the eigen library is optimized to its fullest, and it's also support something called immutable matrices, which we'll come to in a few seconds. If you can, write your code in a vectorized way. Why? We'll see in a bit. But even without the features that are to come, the vectorized code can be faster even now. Like the exponential function, the XP function, the log function, I think is also a few percentages faster if you use vectorized code. But most importantly, if you write vectorized code, if possible, your implementations will be more future performance proof. So you will get the future performance for free. If you are using AWS in order to run your models, we do advise you to look at using the ARM instances, so the Graviton instances, C6G. We have done some research on done some testing comparing those instances to the C5 Intel instances, which are like similarly priced. And the speedups, if you use multiple chains, at least 2, but if you use 4 chains, the speedup with the ARM instances is going to be up to 3 times. So at least 50%, even for simple models, but even more so if you use reducedsum, so the within chain prioritization. So if you are using AWS instances, make sure to test that out. And lastly, because we know we have a lot of Windows users, if you are using Windows, make sure to try Windows subsystem for Linux, which is a actual part of Windows. So it's kind of like a virtual machine inside of Windows that runs Linux. Compiling and running the same model on the same system inside of native Windows or inside the Windows subsystem for Linux can speed up your. If you use the subsystem for Linux, you will see like at least 50% faster, but sometimes even up to 2.5 times faster by simply just switching, no other changes done. This is done because of the tool chains that we can use on Windows natively are simply not that efficient. Okay, so now to the fun part, which I know most of you are waiting for, the future features. Most of the future features are discussed in the design docs repository. If you are interested in discussing them, contributing them, making ideas, be sure to check that out. First, we're going to look at a few of the language features, which I'm going to again show in the code module, the Visual Studio Code. So let's look at the closures first. So if you remember the ODE interface before, you can see that now the ODEs have no user-defined functions. Because the user-defined function is defined inside the transform parameters block. You can see that you didn't have to define any of the arguments. You can just use KM, which is the global parameter. You can use the data. You can use transform data directly, which is all really, really nice, at least in my opinion. There's no performance benefit to be here. The benefit here is mostly readability, usability, and maintaining the model. The next feature is tuples. Okay, so tuples. This is also really close to being in Stan. So you will be able to define a tuple of simple types, array types, combine tuples within tuples, which will also enable having a function SVD instead of having 2 functions for the lower and upper part. We could actually return both, which I know some users are really excited about. And also user-defined functions will be able to return multiple arguments, multiple variables. Complex is a feature that's already in Stan, so this is also like not future, this is the present. The complex, currently you can use scalar, complex numbers, and arrays. Vectors and matrices are not supported. Vectors and matrices are the stuff we're really excited about because that's stuff that's going to enable stuff like fast Fourier transform. So that's something we're really looking forward to. But you can use now currently the complex numbers scalars. Lastly, a feature that I know a lot of users are excited about is ragged arrays. So you will be able to define a ragged array, specify, let's say, the first element has 3. The first dimension, so you have 3 elements and also then 4. So you will know that you no longer have to define an array of same length in all dimensions, or all rows will have. So not all of them will have to have the same length. This feature is unfortunately not as close as the other 3 I mentioned, but it's still in the works. The design was approved. So, but we still for this one we're probably not going to be able to implement this year. But I know this is a feature that's really important for a lot of our users. So the next one is a performance related which is partially why I had to explain all the details before. So we currently represent a vector of of parameters in memory, so that the first element is a value, the second one is the adjoint, then again a value of the next element, the adjoint of the second element, then again the value of the third element, the adjoint of the third element, and so on. Turns out this isn't really performance. This isn't really good for performance. Why? Because in most cases we're not interested in the value and the adjoint at the same time. We're mostly interested in the entire vector of matrix. So it's the value of the entire matrix or the adjoint. So we need something like a var of two matrices. So we need to define value as a contiguous memory, the same as for the adjoint. In order to do that, we had to significantly overhaul the StandMat library. We had to make the var class templated. So this new class is called var value. So var value double is essentially the same thing as the current var. But then you can define a var value of matrices. So I apologize. This should be double here. I apologize. So that means that you have two matrices, the first one representing the values and the second one representing the adjoints. This meant we had to rewrite a significant part of the math code, of the math library, but it's worth it. The functional evaluations and gradient evaluations are up to 3 times faster, and for some functions are a lot more, even a lot more than that. The math support for this feature is mostly complete. So if you would like go generate the C++ model and manually change it, you could actually use this feature. The problem is it requires careful StandC3 optimization, because we can't just use these immutable matrices everywhere. Because if you use indexed code, this approach will be slower. Why? As I said before, if you need the value and the adjoint together, this is going to be a bit slow. But this is why I said before that you need to write your code vectorized. Because if you write it vectorized, you will be able to use this feature immediately. Okay, so I'm going to quickly now, though, seem that I've spent too much time here. So the opencl support is similar to how the immutable matrices are handled. So we have a matrix CL object which handles container of data variables on the GPUs, on GPUs, and we then have a var value matrix CL, which can handle parameters on GPUs. So you can specify, these are A and B are matrices on the CPU. You can specify 2 matrix CL, copy them to the GPU, compute the product or whichever function you want on the GPU, compute the result, compute the gradient, and the gradient will trickle back to the output. Oh, sorry, the input variable. This is what it, again, this was again a significant overhaul, or not an overhaul, but an addition, and it makes a lot of the models significantly faster, because you can see here up to 60 times. You can also run a lot of chains, so a lot more chains than on a CPU. All LPDF, LPMF functions are currently supported in command stand, so you can use them already. But we need another step in order to use more functions. So the math library supports them, but we need a safe way of generating C++ that uses those without erroring during compile time. So that's the final step we need to do before we make this GPU backend really, really, really useful. Okay, then two projects I'm going to just quickly skim through because but I want to mention them because they are really, really exciting. One is embedded Laplace approximation. As you can see, the authors are really the who's who of Bayesian statistics: Charles, Aki, Dan, Raj. Oh, really, really. This is going to be really exciting. This is really exciting. So what you can do with this embedded Laplace approximation, you can marginalize some of the parameters and run MCMC on a better behaved parameter space, and then recover them later in a generated quantities block. Example is shown here. So this is the marginalization, and this is the retrieval step in the generated quantities. Finally, the Pathfinder algorithm, which is VI, so variational inference algorithm, that has the most important, or one of the most important features of it, that you can evaluate the elbow values in parallel. So the algorithm is embarrassingly parallel. And even without that, it requires 1 to 2 orders less log density and gradient evaluations, which makes it really exciting. You can use this algorithm as a VI algorithm, and also like the first part of the warm-up in HMC or dynamic HMC, whatever you want to call it. The links are on the slides, which hopefully I will post somewhere. And finally, I want to thank everyone for your attention. If you followed up with me through the entire presentation, and also want to thank all of our developers, all our users for their bug reports, feature requests, and finally the sponsors that donate to the STAN project. If you want to help us by contributing code, documentation, or anything else, be sure to check out our GitHub page.
That's great. Thank you so much, Rock, for this presentation. We have time for a few comments, not a few questions, not too many.
Yeah, I was a bit long.
So. No, but it was great. It was great overview. So appreciate that. So I'm going to start from the top. And this first question from Jose is asking, I got the intuition that Stan did mixed AD, both backwards and forwards AD, but the slides only mention adjoints and reverse mode AD.
So yeah, so StandMath implements both the reverse mode and the forward mode, and additionally also mixed mode, but Stan only uses reverse mode. I think you might use them in certain features, but in general, the gradients are evaluated with reverse mode AD.
Okay.
That's the 2 questions, yeah.
So next question from Ellen, is command stand R going to be released on CRAN?
Yes, we are in the final stages, hopefully this year. We'll see how much time we'll have, but we are very close. You should probably expect the release candidate for the 1.0 version next week, maybe in 2 weeks. And then we'll see how much feedback we get, how much bug reports we get, and then we'll hope to release our CRAN.
Next question from Bruno, I think in reference to some of those specialized GLM functions. And the question is around.
Yeah, I don't think so.
Okay.
I don't think so, yeah. Unfortunately. Okay. Hey, Bruno. Bruno is also a user that frequently reports issues and reports fixes, so we're really glad to have him.
Okay.
Shout out.
So another question from Jose is asking how much performance are left on the table by not using specific CUDA libraries, but opencl.
Yeah, that's also a common question. So the question there is how much. So the CUDA libraries are fine-tuned for specific architectures. So I would say that for like LPDF, LPMF functions, we're not probably losing more than a few percents here and there, which means like you would get from 10 minutes to 5 minutes, or not even that. So we are losing some of it, but we are using opencl for other reasons, because it supports a larger, more GPUs. So, and because Stan requires double precision, it's important to also support other GPUs, because AMD is focusing more on double precision as opposed to Nvidia, which is focusing more on deep learning and thus focuses on single precision, half precision even, which isn't really applicable for Stan.
And a question from Alan is asking, are nlearn Pathfinder available already or in the roadmap? I think it's in the roadmap,
Pathfinder, I think, is in the last stages of making it like a prototype available via command stand, so like a branch of command stand. I think I saw Steve working on that recently. I'm not sure how close is that, but I think they are already a few models that you can use it. They have tested with. I think the Pathfinder should be available at least on a branch of command stand within the next month or so. Hopefully, but Steve will probably a bit better on that.
And now the question from, I would say Joran, maybe is the right way to pronounce that name. Sorry if I messed that up. He has some old models with MapRect, or within chain parallelization, is it worth translating to reducedsum?
So if the output of the MapRect functions that you use are a single, so you need a sum. So if you run a MapRect and then finally sum the results of the MapRect, then it definitely, yes, use reducedsum. So reducedsum only works if your output is a single value, but that mostly is mostly the case because we're usually computing the target function. I would say yes, because the reducedsum is much easier to read, much easier to maintain, and I think if you are using the same version, probably you won't get much of a performance boost, but you definitely won't get a slowdown.
Then another question from Bruno regarding this feature that's been hanging around on forums for a while, right? And they asked to do with specifying the gradients of customer PDF functions.
So this means specifying the gradients in stand. So
correct. Yeah, I'm sure that's what he means. Mm-hmm.
Yeah. So that's I wouldn't expect this one to be here soon. We are debating it frequently. There are a few things we need to carefully do in that case. So I would say probably this one is a bit more into the future, but still in our plans.
Great. Well, that's all we have time for. So let me once again thank Rock for joining us. It's getting pretty late. Slovenia, thanks for hanging around. It was a terrific talk. Really appreciate it. And also thanks for putting all these amazing improvements into Stand. We're big users of it. And I know it was not just you, but you also contributed. And so we all thank you for all the great work. Thanks, everyone. We'll see you back in December. We have another great talk planned for you from a person who knows a thing or two about climate science. So see you in December.